Hi, welcome back to Math 111 College Algebra at Blue Mountain Community College. My name is Anne-Marie Harden, and I'm your instructor in this course. We're going to go ahead and keep on working through Chapter 1, and we're going to talk about Section 1.3, which is about graphs of equations. Now, last section we talked about relations, and it's a really short section. And we just introduced the fact that relations kind of give us a tie between an x value and a y value. Now we're going to talk about graphs of equations. And a graph of an equation represents the set. It's a picture. It's a picture of the set of all xy pairs that will satisfy the equation. In other words, it's the set of all xy paired values for which the equation is a true statement. Here's an example of what we mean by that. We want to determine if the point 2, -1 is on the graph of x squared plus y to the third equals 1. How do we do that? Well, one way we can do this is we can just plug in the values. So if I plug in 2 squared, if I plug in x equals 2 to this equation, what I'm doing is I'm saying, all right, well, 2 squared plus -1 to the third power. And then I'm asking, does that equal 1? Because my equation says it does. And if this point is on the graph of that equation, then it will. So 4 is 2 squared. 1 -1 to the third power is -1. That is 3. That's not 1. So the answer is no. The point 2, -1 is not on the graph. Right? That's one way we can check. There are other things we can do. We can use our calculator. Now, your graphing calculator can only graph y equals. I know, it's a bummer, but it's the truth. In order to graph anything on your calculator, you first have to solve the equation for y. So that's what we did here. We isolated the y cubed, and we took the cube root, and we got y equals the cube root of 1 minus x squared. You plug this into your graphing calculator, and you can make your graphing calculator give you a table of values. And then you can say, okay, well, let's look at x equals 2. X equals 2, y equals the cube root of -3. Or sorry, negative cube root of 3. And the negative cube root of 3 is not 1. So, a y of -1 does not go with an x of 2. The other thing you can do is you can look at a graph. If we look at a graph, we get -2, not -1. One thing you can do for something like this, Desmos is a really handy tool for this. Let's go take a look at Desmos. Let's just go out here. And we'll start graphing. And let's plug in this equation. Now, the cool thing about Desmos is you can just type in x squared plus y to the third equals 1. And Desmos will graph that for you. And then you can say, and then the other thing you can do is, since we're checking a specific point, we can plug in, let's see, what is our point? 2, -1. So we can check and see, we can ask Desmos to graph 2, -1. Oh, looky there. 2, -1 is not on the graph of my equation. Now, we already talked about what that means. What that means is that if I plug in x equals 2, y of -1 does not come out of my equation, right? Okay. All ways to check and see if a point is on the graph of an equation. Any line that is on, any point that is on this line that is formed from a graph of this equation must, by necessity and definition, result in a true statement if we plug it into that equation. We've got some special points we're going to talk about. And we're going to talk about these a lot during this term. We're going to talk about the x-intercepts. The x-intercepts of a graph are the points where the graph, the curve that represents the set of points that satisfies that equation, crosses the x-axis. Now remember what I told you last video. What did I say about the x-intercepts? Maybe it was 2 videos ago. Might have been the very first video. It was actual course material. I think it was. What I said was, any point on the x-axis must have a y-coordinate of 0. So to find these x-intercepts, we're going to set y equal to 0 and then solve for x. We're also going to talk about the y-intercepts. The y-intercept is the point where the graph crosses the y-axis. For this particular function, or equation, the x-intercepts occur at -1, 0, 1, 0, and 0, 1, because on the y-intercept, to find the y-intercept, we set x equal to 0 and solve for y. Okay, so let's summarize that. The steps for finding the intercepts of the graph of an equation. When we say find the intercepts, we mean find the x-intercepts and the y-intercepts. And there might be more than 1 or 2. Think back to, well, we'll get into that later. So x-intercepts of a graph, we set y equal to 0 and then we solve for x. To find the y-intercepts of a graph, we set x equal to 0 and then we solve for y. Let's try it. Let's find the x-intercepts of the equation that we've been working with. X squared plus y to the third equals 1. Now we already know what they're going to be because we've looked at the graph. But let's go ahead and do this algebraic. Let's start with the x-intercept. To find the x-intercept, we set y equal to 0. That gives us x squared equals 1. We take the square root of both sides. Remember, we have to take both the positive and negative roots because the square root has an even index. The index is the number in front of the radical, right? The square root's got 2, an index of 2. That's an even number. So when we take the square root to solve an equation, we have to take both the positive and the negative roots. So we have 2 x-intercepts, one at -1, 0 and one at 1, 0. So on the y-intercept, y-intercept occurs where x equals 0. Like in x equals 0, we get y to the third equals 1. That only happens where y equals 1. We don't have to take positive or negative because -1 to the third power is not 1. -1 to the third power is -1. Up here, we have to take the positive and negative roots because -1 squared is 1. In other words, we have 2 numbers that we can square to get 1. Okay? Only 1 number do we cube to get 1. So our y-intercept is at the point 0, 1, which we already knew because we looked at the graph, right? Okay, we're just verifying and demonstrating the algebraic solution here. So those are the intercepts. Remember symmetry for points? We care more, as much, about the symmetry of graphs. So we're going to talk about some ways to test an equation to see if it is symmetrical. Okay, this gets a little confusing, so think about it, make sure it makes sense to you, and we will do an example. But you want to do some of these to make sure that you understand what we're doing here. When we talk about symmetry about the y-axis, let's take a look at that graph for a minute. If you have this printed out on a piece of paper, and if you're struggling with this, I encourage you to go ahead and print out this graph. But if you print it out on a piece of paper, envision folding this thing along the y-axis. you can see that if you fold it up, it's going to lay right on top of itself, just like my hands lay right on top of themselves, because my hands are actually symmetrical, mostly, right? So we know this graph is symmetrical about the y-axis. Is it symmetrical about the x-axis? Well, that would be like folding my hands this way. My hand, no, see, my fingers and my palms don't line up, so not symmetrical about the x-axis, because if I fold this piece of paper over onto itself across the x-axis, my graph does not lie on top of itself. I get not the same thing, right? So here's how we test this algebraically. To test for symmetry about the y-axis, remember with points, what we were looking for to see if points were symmetrical about the y-axis? We were looking for same y's and equal but opposite x's, right? We use that same idea to test an equation for symmetry. We replace our x's with negative x and simplify. If we end up with the same thing that we started with, then our graph is symmetrical about the y-axis, just like our points. Think about now, let's talk about the symmetry about the x-axis. Think about what we were doing for points. 2 points are symmetrical across the x-axis if their x values are equal and their y values are equal in magnitude, so same number, but opposite signs. What we do here to check that is we replace our y's with negative y's. Simplify. And if we get back to what we started with, then our graph is symmetrical about the x-axis. Now, graphs can also be symmetrical about the origin, and we test for that by replacing both x and y by their negative x, by their negatives, and simplifying. Let's look at an example. Our same equation. Okay, we're friends with this one. We already know the answer. That's because we've looked at the graph, but let's demonstrate how we test this algebraically. So we're going to test this equation for symmetry about the y-axis, the x-axis, and the origin. I just told you what we're going to do. Let's start with the y-axis. To test for symmetry about the y-axis, we replace x with negative x. So we replace x, our equation is x squared plus y to the third equals 1. Replace that x with negative x squared plus y to the third equals negative 1. And simplify. We get x squared plus y to the third equals 1. Is that what we started with? Yeah. So this graph is symmetrical about the y-axis. You knew that, right? We look at this graph, and it is symmetrical about the y-axis. If I print this out, and I fold it across along the y-axis, my lines lie, my 2 halves of my graph lie right on top of one another. This is symmetrical about the y-axis. Is it symmetrical about the x-axis? Well, the graph tells us the answer, but let's check it algebraically. Let's replace my y with negative y. Do nothing to the x. And simplify. So x squared plus negative y to the third power is going to give me x squared minus y to the third equals 1. This is not the same thing as what we started with. What we started with is x squared plus y to the third equals 1. So no, this graph is not, absolutely not, symmetrical about the x-axis. Again, we already knew that, so it's good that our algebra matches with what our eyes tell us. Okay, let's check for the origin. We know this too, right? Replace negative x replace x with negative x and y with negative y and simplify. We end up with x squared minus y to the third equals 1. Not the same thing as what we started with. What we started with was x squared plus y to the third equals 1. This graph is not symmetrical about the origin. Not hard, right? You just have to remember a little bit of algebra. You do need to remember the technique. Okay, that's it for this section. Work on your homework, and I will talk to you soon.